Well, here we are again. Welcome to the Thursday night presentation, the Nottingham Astronomical Society. I hope you've all been well and enjoying the relatively sunny weather today, although it's quite mixed over the last few days. And tonight, before Chris gets started, I'll just let you know what's coming up. So the 15th of this month, we'll have the Plumtree meeting, although we had hoped to actually hold it at the observatory and show you what we'd been doing since then. But unfortunately, the restrictions won't be lifted in time. So we're going to see if we can do it virtually and present it that way and include in it a history of the observatory and all the work that's been done on it before and currently too. Anyway, that's something to look forward to. The next main meeting isn't a meeting at all. It's a barbecue in August, the 7th of August at 5 p.m, hopefully, unless everything goes rainy again. So I'd really love you all to come along and see that. Come and have a look at the new telescope, the new observatory, eat, drink and be merry and have generally good time and meet up in person. One other thing, the journal hasn't gone out yet this week. It's all been done, so it's nothing to do with Roy's fault. It's just that Lee's been on holiday, so hasn't been able to send it out yet. But it will probably be out by the end of today. At least that's what we hope. So with the administrative trivia out of the way, I'd like to welcome Chris Arridge to the Society. It doesn't seem very long ago since he was last here. In fact, it was September, I think, when he was talking about Enceladus. Was that right? I think so. Anyway, Chris comes virtually from Lancaster and will be talking to us about the JUICE mission, which I heard about many years ago. And at the time, I forget who was talking about it. It might have been Michelle Doherty. But I remember introducing it and saying, JUICE, silly name. I'm sure we'll come up with a better one. But anyway, it seems to have stuck. So there we go. So with that out of the way, over to you, Chris. And you'd like to unmute and share your screen. And over to you. Thank you very much for coming to visit us.
Thank you. Good evening. Just put my my slides here. I can already see a cat coming towards me in my peripheral vision, so you might end up with that appearing at some point. Okay. Okay. Super. So can you? Okay, so I can see Julian's said that you can see it, so that's great. Okay, so thank you for having me back again. It's like Julian said, it feels like yesterday. So last time I talked to you about Enceladus and the Cassini mission, and this is. More of the same. That's not a good advert. There's going to be a familiar flavour to this, in that we're sort of we're diving down underneath the surfaces of satellites in the outer solar system. And so this picture that you're seeing here on my title slide is one of the artist's impressions for the JUICE mission. And what I want to do today is to give a flavour about the history of the mission. So Julian talks about the first time he'd heard about the mission. I can offer some of my own memories of that. Talk to you about the genesis of the mission and how it evolved over time. What the mission is about, and where we're sort of at now, and what the challenges about with this specifically with this mission. So yeah, the name is a bit. The name is a bit strange. It sounds like it shouldn't mean anything at all, but it stands for Jupiter Icy Moons Explorer, and it's a mission to the largest natural satellite in the solar system, Ganymede, but also is a mission to Jupiter itself and Jupiter's planetary system, as I'll talk about. We are going off out to Jupiter, and when I spoke to you last, we were obviously at Saturn and looking at Enceladus. Here we're going off out to Jupiter, And the mission is concerned with Jupiter and the Galilean satellites. The mission will have a couple of flybys of Europa, but we really will focus in on the outer two of the Galilean satellites, focusing on Callisto and Ganymede. And you can see here how large these satellites are compared to other satellites and other bodies in the solar system. So these bodies are all to scale. So you can see, Ganymede is larger than our own moon, for example, larger than Titan at Saturn, and actually not too much smaller than Mars itself. And Ganymede, in fact, is bigger than Mercury. So these are substantial planetary bodies, and there's something around. These are not just satellites, benign, boring satellites around a much more interesting world. These are very interesting places to go and look at in their own right. And that's a big thrust of JUICE, and it's a big thrust of some other missions as well, including Europa Clipper. So not going to Jupiter and, oh, hey, we can look at these satellites while we're there. It's let's go to Ganymede and look at Jupiter while we're there almost. So that's sort of a bit how I think about this. So what is JUICE in a nutshell? And again, I'm showing you some more slightly older illustrations here on the right, and some of the more modern designs on the left here on this slide. So what is JUICE in a nutshell? Well, the idea behind JUICE is to explore the emergence of habitable worlds around gas giant planets. And so here what we're doing is trying to characterize Ganymede, Europa, and Callisto, these three predominantly icy satellites, as planetary objects in their own right, not purely as the children, if you like, of gas giants, but what is characterized as planetary objects in their own right, and also then as potential habitats. And then the secondary goal here is to explore the Jupiter system as an archetype for gas giant planetary systems. So use it as a template to see what can we learn about gas giant systems, planetary systems in general, by looking at the Jupiter system. Just want to, before I move on to talk a little bit about the mission, what's this idea about potential habitats, and why we're focusing on this? And particularly if you didn't see the talk on Enceladus, this might be a bit of a strange idea. So the idea with this is that for a long time we had this idea of what was the idea of a habitable planet. So Earth is obviously a habitable planet, and we think, well, Earth is sitting in a Goldilocks zone with respect to the sun. It's neither too close to the sun, so it would be too hot for life, and it's also not too far away from the sun, so it would be too cold for life. It's just in the right spot. Or just in the right range of distances from the sun to make Earth a habitable and a pleasantly habitable place around the sun. And you could do these sorts of exercises for other types of stars. You can think about, well, what might that location, what might that Goldilocks zone be around an M-class star, around an A-type star. You can perform this exercise. You can look at how much insolation there is from the star versus distance away from the planet. So that was a sort of a prevailing view for a long time. And then when we started to go and look at some of these outer planet systems in detail, we started to see these satellites were very interesting places. And the thing about the Goldilocks zone is we're sort of thinking about, well, we want a place where there's liquid water, we want a place where there's a source of energy, we want a place where there is a source of raw materials for chemistry, so nutrients for chemistry. And that's what we've realized by looking at places like Europa, looking at places like Enceladus and Titan, is that that sort of narrow zone close to a star is not the only place you might think of looking. So at Europa, as we're going to see, we've got good evidence for a subsurface liquid, or at least semi-liquid ocean. And there we've got a source of liquid water. We have a source of energy that's there keeping this interior warm. And we've got good evidence that that liquid subsurface ocean is salty, and so we've got a source of nutrients there. So we're expanding our ideas about what might be habitable and what might not be habitable. So what's the idea behind what's the mission profile, as we call it? What's the design of the mission? So we have a launch next year in June of 2022 with a planned arrival at Jupiter in 2030. These are on the right here. These are sort of some sketches of potential designs for the spacecraft, and you can see that the sketch that I showed you a few slides ago corresponds much more closely with the center design here, and that was a result of a competition for who would design and build the spacecraft. Once the spacecraft has entered Jupiter orbit, so we have this phase here called JOI, that's Jupiter orbit insertion. So we go into Jupiter orbit, and then we have a number of orbits going around Jupiter. We have these perigeoves, so the closest approaches to Jupiter. So we go into Jupiter orbit, and then we have a long period before we get to our next closest approach to Jupiter. So you can see that as we come into orbit around Jupiter, then we're flung into a very large orbit that circles around the planet for a long time before we have our next closest approach to Jupiter, and then we enter into a much more sort of regular and shorter period set of orbits around Jupiter. And as we're going around Jupiter, having these orbits, we have encounters with the other satellites. So we've got these 2 encounters with Europa, multiple encounters with Ganymede, lots of encounters with Callisto. And then you can see that we get to this point here in 2032, in September 2032, and the perigeoves stop. And that's not because the mission's come to an end, it's because JUICE has now entered orbit around Ganymede. So that will happen in September 2032. JUICE will go into orbit around Ganymede, initially in an elliptical orbit, then that orbit will circularize and end up basically touching down on the surface of Ganymede at the end of the mission. Now, the things that make this a hard thing to do, or a couple of specific things that make this hard to do, are that it's a very challenging radiation environment. So if we got a spacecraft in orbit around Saturn, for example, like Cassini-Huygens was. So Cassini is in orbit around Saturn. Saturn's radiation belts are strong, but they're not terribly intense. It's fairly easy to shield the electronics and the systems of the spacecraft from that radiation, from those radiation belts. Jupiter's an entirely different kettle of fish. Jupiter's got the most intense radiation environment of any planetary object in the solar system. And that's a very difficult challenge for spacecraft, for building a spacecraft that will survive long enough. And we've seen that with Juno, and I'm going to talk more about that later. The other challenge with this is that JUICE is solar powered. And many missions are solar powered. You see many missions at Mars and Venus, and of course around the Earth that are powered by sunlight. But the problem is at Jupiter is you have over 5 astronomical units from the sun, so sunlight is 25 times weaker. So you need enormous solar panels to run all of your electronics on board the spacecraft. So if you think, oh well, I'm in orbit around the Earth, I need a solar panel that's 4 square meters in order to generate the electrical power I need. And then you take that out to Jupiter. Well, that's 25 times 4 meters squared. So it rapidly scales up quite big. So you could think about, well, you might have solar panels on your roof as part of your own energy needs, and you imagine making those 25 times bigger. That's the sort of challenges we're dealing with here. So that's a big challenge, and so we challenge them. So we need these enormous solar arrays to provide the power. The other challenge, and this is sort of going hand in hand with the radiation aspect, is that we have to worry quite carefully about planetary protection. The whole idea with planetary protection is we don't want to inadvertently contaminate other planetary bodies in the solar system. So let's say, for example, that we built a spacecraft and there was some bacteria or other form of terrestrial life on there, and we accidentally crashed that into Europa. So the surface of Europa is very icy, but there's lots of structures there on the surface, geological structures that we interpret as evidence of movement of material between the surface and the subsurface. So that you crash a spacecraft here, for example, there's a chance that the remains could, and potentially therefore the material that's been brought from Earth to Europa, that's dragged down into the subsurface. And so I often like to think of this fairly glibly as, let's say in 10,000 years, we drill through this ice and get through to this subsurface ocean that we suspect is underneath the ice at Europa, and we find dolphins in there, and someone turn around and say, well, they're not genuine European dolphins. They were taken there by that spacecraft called JUICE or whatever in the 2000s. So that's the sort of the glib answer, and of course it's very relevant for Mars. It's looking for evidence of either extinct or extant life on Mars is a top priority scientific target. And I'm not sure many of you, maybe you remember the Allen Hills meteorite in the 90s. And there are lots of possible interpretations for what you find. And the question is, well, you don't want to be stuck between thinking we've exhausted every possible option here, every possible inorganic option here to explain this observation. The only true thing that we can think of is actually biological in origin, and then actually to say, well, the spacecraft wasn't decontaminated, or that previous spacecraft wasn't decontaminated. So that's the basic idea with planetary protection, is we don't want to be contaminating our local neighborhood. And that, depending on where you're going, it puts different constraints on your spacecraft design. So if you were going to drop an entry probe into Jupiter, for example, the requirements on you decontaminating your spacecraft are a lot less than if you were going to land a rover on Europa or a rover on Mars. You can safely sort of say that dropping a probe into Jupiter, anything that is from the Earth that survived, anything biological from Earth that survived, will be utterly destroyed by that process of re-entering Jupiter's atmosphere and going to depth. Whereas you land a rover on Mars, you're not guaranteed that it won't be destroyed, assuming the thing doesn't get blown up on impact. It will survive on the surface. It will be there on the spacecraft or inside the spacecraft surfaces. So there are very different limits depending on where you're going, and also the nature of the planetary body you're going to. So is the planetary body thought to be basically a dead world, like the moon? We don't think necessarily that the moon is a habitable volume, and so you wouldn't necessarily worry as much about decontaminating your spacecraft to go to the moon as you would do if you're going to Mars, for example. So this places a lot of constraints on how you build your spacecraft. There's costs associated with it. You've got to decontaminate the thing. And one of the ways that's often done is with radiation, that you can use some of this radiation that's naturally in space to decontaminate your spacecraft. But if you're going to an environment that's radiation rich and you're naturally shielding your spacecraft to prevent that radiation getting inside, then you can't benefit from that decontamination process, and that's part of the problem with JUICE. I'll get to that towards the end. So, how did JUICE evolve? How did we get here? So, JUICE was originally called Laplace, and this is when I first encountered the idea behind the mission. I was still a PhD student when I first heard about this mission, and it was proposed to the European Space Agency's Cosmic Vision Large Mission Program. I'm going to touch on this again towards the end. And originally, it called for a mission to explore the Jupiter system and its moons, pretty much as we have with JUICE now. What happened after that was that it evolved a little bit. So it evolved into a potential bilateral mission. NASA were really interested in the Jupiter system. They were particularly interested in Europa. And so the two agencies got together and said, hey, we could do something. We can get benefit from having two spacecraft at Jupiter at the same time. And this had happened before. This had happened with Cassini and Galileo. Galileo was still in orbit around Jupiter when Cassini did its flyby of Jupiter on its way out to Saturn. So there's a lot of scientific benefits from having two spacecraft in a system at the same time. And so the two agencies said, well, let's get together, let's do this, let's have a bilateral mission. We'll send two spacecraft. We'll call it the Europa Jupiter System Mission, EJSM. NASA spacecraft is going to go to Europa, and the European spacecraft will go to Ganymede. And then over time, this was studied quite intensely, and I was part of instrument proposals that would build sort of sibling instrumentation, so very, very similar but slightly tuned instrumentation, one to go on the Europa mission to Jupiter, to Ganymede, sorry, and one to go on the NASA mission to Europa. But ultimately funding changes happened within NASA, and the Europa component ended up being dropped. And so ESA decided to go ahead with it, and we had JUICE, which was just a Ganymede orbiter run by ESA. So that's the sort of tortuous journey of JUICE, and it sits in a history of exploration of the Jovian system. So starting with Pioneer 10 and 11 in the 1970s, there was a period where there was another mission that went and looked at the Jupiter system. This was Ulysses in the 90s. We had Voyager in the 80s. And Cassini and New Horizons did flybys of the Jupiter system as they were going off to Saturn and Pluto, respectively. But the thing that really set us on this journey was Galileo. And Galileo was launched in December of 1995, and it had its end of mission in 2003 with a controlled crash into Jupiter. And this, the Galileo mission gave us this evidence that I mentioned for Europa having this subsurface ocean. But in some senses, Galileo was sort of a disappointment in that there was a technical failure. And so we didn't get back as much data as we wanted. So this is a photograph of Galileo in construction at the Jet Propulsion Laboratory in California. And this was to be launched from the space shuttle, and to fit Galileo into the space shuttle's cargo bay, they had to do something clever to get the antenna, the high gain antenna, to fit in the cargo bay. And the idea behind this is that the diameter of your antenna determines to a large degree how much data you can get back. It basically controls the data rate. So if you've got an antenna that's a certain width and you double it, you can get an awful lot more data back. So your megabits, like you would have for your home broadband, goes up quite significantly as the antenna size goes up. So basically, the bigger the antenna you can pack on your spacecraft, the more data you'll get back. And that's sort of a bottleneck now, because our instruments can take data faster than we can send it back to Earth. So they thought, well, rather than having this fixed dish, if I just back up a second, so this image of Voyager, you can see the high gain antenna here, you can see the high gain antenna here on Cassini. These are fixed dishes, and so that limits how you launch that into space, because that dish has got to fit in whatever you use to launch it into space. So for Galileo, they said, well, let's make the antenna fold up. Let's make it like an umbrella. And that's what these ribs are here. So this is like an umbrella upside down. And when Galileo was in space, the idea was it would unfold, and the rim of the umbrella will be out here, forming this antenna. And unfortunately, this didn't deploy properly. And this artist's impression on the right-hand side here shows you how some of these ribs got stuck on the mount up here. So some of these ribs here got stuck on this sort of gold-colored piece here. And so basically this antenna didn't work properly. And so they were left at using a much lower power antenna. So a bit like going from, say, your fiber broadband that you have now, and you've got to go back to 56K dial-up, right? So that's the sort of challenge. You're expecting megabits a second or hundreds of kilobits a second, and you're suddenly down by orders of magnitude. So that was a real challenge. So we didn't get back the data that we wanted, but there was lots and lots of discoveries made with Galileo. They did lots of very clever things to maximize how much data they could get back. So a lot of the error correcting algorithms that are now used in standard telecommunications satellites, they were tested for the first time on Galileo, because they were trying to make the best use of every single bit that they could send back. They arrayed lots of antennas on the ground with the NASA's Deep Space Network. They arrayed many of them together to basically give us a much larger effective antenna diameter so they could get a lot more data back. They did all sorts of really clever things to squeeze everything they could out of this spacecraft. But it still left lots of questions. It gave us lots of very interesting things like the subsurface ocean and more things I'm going to talk about. But it was limited, and it made people want to go back. And the mission that we've got there at the moment is Juno. So this is a solar-powered spacecraft that's in a polar orbit around Jupiter, looking at the deep interior of the planets, the clouds of the planet, and I'm sure you've seen lots of photographs and images from Juno, and some of you may have even seen some of the recent images from the flyby of Ganymede that Juno did. So that's the spacecraft that we've got there at the moment. And one of the targets for Juno is looking at the aurora of Jupiter. So this is an image of the aurora of Jupiter in ultraviolet light. This is from the Hubble Space Telescope. And really, Juno is going right over this aurora, looking right down on it, like you might do for many Earth missions that have gone over the poles of the Earth and taken pictures of the aurora looking down. If you think about the images taken of the aurora by from the ISS, you get a sense of the not just the detail that not just the extent of it that you see, but the detail as well. That's one of the things that Juno's been doing. So let's just think a little bit about the science that we want to do with JUICE. And so we start out with Jupiter. It's the center of the system. And I said at the beginning, we're thinking about this as an archetype for gas giant systems. And in some ways, people have talked about Jupiter as being like a miniature solar system in miniature. You can make a similar argument at Saturn. You've got a very large central object. You've got some rings around it that maybe are somewhat similar to an accretion disk around an early star. And you've got some embedded satellites that maybe represent the planets going around a star. So we got this sort of solar system in miniature. And really, we want to know how that system works together. How do all of those parts of the system fit together and sort of talk to each other, if you like? How do they interact with each other? And so one of the drivers here for studying gas giant systems is that they tell us something about how they can tell us something about how the solar system might have formed. Excuse me. So this artist's impression here is showing you a phase of the solar system formation. We got a newly born star there. We've still got some material left over from solar system formation, and all of this gas and dust is being blown away by the radiation pressure from the star, and leaving behind the planets that have formed in its wake. And the idea here is that if we can sort of figure out what these planets are made of, that might give us some hints as to what this overall cloud was made of, and also where these bodies formed in that cloud. Were they really, really close in, where the cloud might have had different properties, were they really far out, and so on. So they give us hints into a process that we can't see it directly. We can't go back in time and see it directly. The only way we can investigate that observationally is either going and sampling solar system bodies, or actually observing the same process, or what we think is the same process going on around other stars. So this is a vital piece of the puzzle, piece of that jigsaw. And so we end up sort of starting to think, well, what's inside of all of these gas giant planets? You know, we can look at the surfaces, we can look at their thin atmospheric envelopes, but actually what's underneath is more indicative, is more reflective of that formation process. And so we end up with lots of these sort of onion diagrams where we see these different layers within the planets. And if we just focus on Jupiter, we've got an outer envelope of molecular hydrogen and helium, a layer of metallic hydrogen inside, and then potentially a rock and ice layer at the very center. Metallic hydrogen doesn't mean that it's actually a metal. What we're talking about here is that hydrogen is under such intense pressure in the interior of Jupiter that it becomes an extremely good electrical conductor. And when it becomes an extremely good electrical conductor, that's what we describe as this state of metallic hydrogen. But that gives Jupiter an extremely strong magnetic field, which is implicated in why Jupiter has this strong radiation environment. So we're really trying to sort of figure out what layers exist underneath. And this is one of the things that Juno is doing. It's looking at some of these layers, looking at the surface layers, but also looking at the gravitational field of Jupiter, which tells us a bit more about the really deep structure. So I like showing this movie. This is a sequence of images of Jupiter from Voyager 1's closest approach, or from Voyager 1's flyby of Jupiter in 1979. I like to show these pictures because they were taken shortly before my first birthday, and so there's a lot of resonance for me. And I you know, they are black and white, but I still think they are absolutely fantastic. And you can see all of the evolution and the activity and you can never get the play button to show when you want it to. You can see all of the activity in Jupiter's atmosphere. And Jupiter's atmosphere is another target for understanding these gas giant planets and gas giant systems. They behave, they're driven, they're forced in different ways compared to Earth's atmospheric system. So we see all of these vortices, we can see these counter-moving flows, we see these different colored layers corresponding to different molecules in the atmosphere. And if we look actually at the temperature structure of the atmosphere, temperature and pressure structure of the atmosphere, we can see these different colored layers as corresponding to these different molecules with ammonia and water and so on, existing at different pressure levels, different altitudes. So you've got a different layered structure of the cloud deck on Jupiter. And there are a whole variety of questions that we want to try and answer at Jupiter. So what drives the circulation and dynamics in the atmosphere? What drives those jets that we're seeing? So not just zonally around the planet, but also what moves material from the poles to the equator and vice versa. And so effectively, we're talking about weather systems here. What drives the weather on Jupiter? And I mentioned sunlight earlier on. Sunlight is 25 times weaker at Jupiter. You've got a lot of energy coming up from the inside, so you're driving this weather system in different ways compared to the Earth, and that gives you a different data point. It gives you a different an object that's working under very different conditions, so you can get a better sense of what weather is and how atmospheres behave. And of course, you've also got different composition of the atmosphere. There's different stuff there. There's different chemistry going on. There's a different vertical structure to the atmosphere. And there's also a lot of energy being deposited into the atmosphere from above. So the aurora that I showed you earlier, that is actually dumping a lot of energy into the polar regions of the planet, which is another source of energy. And this heating up this thermosphere region here, you can see the temperature structure goes down and gets cold as you basically approach the cloud tops, and then the temperature sort of increases a bit in the stratosphere, then it gets very hot in the thermosphere, and we don't understand why it gets hot in the thermosphere. And part of it, we think, is that the energy input associated with the aurora is heating this region. You may have, there was a news article about this over the last week or so that you may have seen, and that's relates to this problem that we're trying to understand. So I mentioned magnetosphere a few times, and so this is another target for JUICE, is to understand the magnetic part of this extended planetary system. When we look at when we look at the satellites and so on, we see solid bodies, we see satellites. We may get a hint of an atmosphere, or we see rings, but we're talking about solid bodies. But there's a whole extra system surrounding that we can't usually see with the naked eye, and that's the planet's magnetosphere. And the heart of the magnetosphere is the magnetic field that emanates from deep within. So I talked about this metallic hydrogen and producing this very strong magnetic field, and that magnetic field creates a bubble around the planet that insulates it, isolates it from the supersonic flow of gas that comes out from the sun, known as a solar wind. And the solar wind is moving at hundreds of kilometers per second, so over 1 million kilometers per hour. And because it's an electrical conductor, it gets pushed and diverted around the planet's magnetic field, forming this bubble that we call the magnetosphere. And you can get a sense of you maybe can't get a sense of the size of this from this diagram, but the sun is around about that big on this diagram. And so many people would call Jupiter's magnetosphere the largest physical structure in the solar system. And some of the observations from Voyager hint that actually this what we call the tail, the magnetotail, may extend 5 astronomical units to Saturn's orbit. So extremely large structure. And Jupiter is more or less at the center of this, and these lines here are the magnetic field lines. Close into the planet, we have magnetic field lines like that of a bar magnet, but then further and further away, they are getting increasingly distorted by strong electrical currents in space around Jupiter. And so this is another target for JUICE. And this is where we end up with these very, very strong radiation belts around the planet. So the consequence of this magnetic environment. And so just to highlight how big Jupiter's magnetosphere is, if you were to look at this, if you could see it with the naked eye, it would be bigger than the full moon. So this is a sort of a sketch in the night sky of how big it would look. 1.5 degrees wide, so wider than an outstretched finger at arm's length, with the moon being only about 0.5 degree. And what this doesn't illustrate is actually, if I just back up a slide, that the size of this, so that sort of sketch that you were looking at, you're looking at it from the left on my screen, but you're looking at it from the perspective of the sun, and that all of that material is going away from the sun and hitting the magnetosphere. But the size of this bubble, the size of this cavity here, changes depending on how strong the solar wind is blowing. If it blows harder, then this whole thing compresses and gets smaller. If the wind eases off, then it expands. And this can happen over the time scale of hours. So if we could see this in the night sky, we would see this contracting and expanding almost randomly over a time scale of hours. It would be quite a sight to behold if you could see it with the naked eye. And so part of that magnetosphere is intimately linked up with the satellites. So you may know that Io is the most volcanically active object in the solar system. And what happens at Io is Io's volcanoes and atmosphere is ejected into space around Jupiter, and it forms a torus, a donut of neutral gas in orbit around Jupiter that's sort of roughly co-located with Io's orbit. And that's, you can see that material there in sort of like this yellow color around Io here in this artist's impression on the left-hand side. So this is Io here. Here is the neutral material that's been ejected by Io. And then once those neutral atoms and molecules are in space, they can be ionized. So we can have sunlight come in that then kicks off an electron and turns it into a charged particle, or indeed another charged particle might come in and collide with it, kicking off an electron, making it an ion. And that forms what we call the Io-plasma torus, and that's in red here. And that is these particles go on, these charged particles that are formed in this region go on to become the radiation belts. They go on to become the radiation risk to satellites. Okay. And so here you can see a snapshot from New Horizons as New Horizons was flying past Jupiter on the way to Pluto, and you can see one of these volcanic eruptions actually going off. This up here is a volcanic plume that's extending 300 kilometers into space above Io. You're looking at it here sort of in a contrast enhanced mode here in visible light. This is the unlit hemisphere of Io. This is the night side of Io. This is the day side of Io. And you can see that again in color here. If we look at this in infrared, you can see the hot sunlit hemisphere of Io. And then on the night side, you see all these heat patches. And these heat patches are all of these lakes of lava on the surface of Io. And then we have this bright heat spot from this volcanic eruption. So a very interesting place. Now, I mentioned about this sort of solar system in miniature, and Jupiter has played a role in our solar system's history, and that Jupiter is a bit like a giant Hoover, and it will hoover up material that gets too close to it. Hoover in the gravitational sense rather than gas. Anything gets too close to it in the heliosphere, it will be gravitationally captured by Jupiter. So in some senses, it can protect the inner solar system from a lot of material that otherwise would go in and bombard the inner solar system. And of course, one of the examples of this is comet Shoemaker-Levy 9 that collided with Jupiter in 1994. And here we can see this comet that got too close to Jupiter, gravitationally captured, and then was torn apart by gravitational tides, separating it into all of these individual fragments that impacted Jupiter one after another, leaving scars in the atmosphere of the planet. And you can see some of those scars here in images from the Hubble Space Telescope, leaving these giant welts. I mean, on this diagram, Earth is about this big, and so we're talking about very large disruption to the atmosphere, very significant disruption to the atmosphere. And this also produced a reaction in the magnetosphere. So this is another image from Hubble, and it's upside down on this presentation. The actual impacts are here, here, and here. But what's sketched on here is a couple of magnetic field lines from Jupiter, and you can see that in the opposite hemisphere, you've got the aurora lighting up on the opposite magnetic field line. And so what we think is happening there is the violence of these impacts actually caused an avalanche of charged particles to rush along these magnetic field lines to the opposite hemisphere, raining down in the atmosphere and causing it to radiate with the energy of those particles hitting the atmosphere. And so the final aspect of this magnetosphere is that Jupiter rotates very rapidly, and so its magnetosphere rotates very rapidly. When I say rapidly, Jupiter rotates about once every 10 hours, just shy of 10 hours. But that's rapid compared to the Earth's sort of more sluggish 24-hour rotation. And so there are many other astrophysical objects that do rotate rapidly and have strong magnetic fields. Maybe not as rapidly. Maybe Jupiter is not as rapid as some, I said he would make an appearance, and he did. Maybe not. Maybe Jupiter doesn't rotate as fast as some of these astrophysical objects, like a pulsar and other neutron stars. Maybe the magnetic field strength of Jupiter isn't as strong as that of a pulsar or neutron star, but it's the closest analogy we have in the solar system. So that's another thing, another reason for us to study these magnetospheres, is that they provide that sort of ground truth for an astrophysical system that we can't probe in situ. Okay, so let's just get close to these Galilean moons. I've talked about the scale, so I won't dwell on the scale here. But just to talk a little bit more about Io and all of this volcanic activity there. So Io is a little bit different to those other 3 Galilean satellites, because Io is very rocky and volcanic, whereas the other 3 of the Galilean satellites are icy bodies. So Io stands out in its composition. And we see these yellow colors here in images from Galileo. And that yellow color is from all the sulfur that's on the surface from volcanic activity. So really showing this volcanically disrupted moon. And it's so volcanic because it's in an orbital resonance with the other Galilean satellites. And what that does is that Io gets periodically squeezed and stretched by gravitational interactions, and that deposits an enormous amount of energy inside Io, keeping it hot and keeping the interior liquid as well. And so there's some evidence that that Io does have an ocean of magma within its surface. And some people have questioned this idea, questioned this discovery, but it's still in there as a potential idea of what's actually underneath the surface. So we're asking these questions not just about what do the surfaces look like, what's going on underneath those surfaces. And of course, Europa is one of these big the big stars of the Jupiter system, amongst the satellites at least. And we see these crisscrossed features with these dark colorations in them. And so what we think we're looking at here is basically almost like tectonic plates of ice, with these contact boundaries between them. One of the leading ideas as to why they have these different colors to the ice is that at these boundaries where the ice sheets are flexing against each other, we can have material coming up from inside and flooding out onto the surface. And so that's the people think, well, that brown stuff then, is that organic material somehow coming up from inside. And so that people are really interested to get sensitive spectrometers on these regions so they can see what's in there, what are the molecules in these zones, what can they tell us about the interior. And so here we have one of these contact boundaries with all of these different geological features surrounding it, and providing potential access to the material that's this liquid ocean that's underneath the surface, where that liquid ocean is in contact with rock. And so we have this model of the interior where we've got some sort of core, we've got a rocky mantle region, and then sat directly on top of that rocky mantle is this subsurface ocean, providing that means for nutrients to enter into the water. Again, starting to think about this question of habitability. So we're really interested in what happens in these regions and what that can tell us about this subsurface ocean. And it doesn't just have to be I've sort of cast this as some sort of idyllic Caribbean ocean, but it could actually be something a lot more sort of frozen. So you've got this idea that it actually could be something that they call it warm convecting ice. I liken this a bit to like a slush puppy, that it's sort of just like a mush, like driven snow type material. We don't quite know which of these models is right, but that's one of the things that we want to try and figure out by going to the Jupiter system and looking at these satellites in more detail. And the response of this ocean to Jupiter's magnetic field is how we know that ocean is there. Effectively, this ocean is if the ocean is salty, it's therefore an electrical conductor. And if we got Jupiter's magnetic field surrounding this moon and changing all the time, then electrical currents are produced in that ocean. And that's actually what Galileo observed when it flew past Europa. It detected the magnetic signature of electrical currents flowing in this ocean that then give us an insight into what's going on inside. So we have this picture then of this rocky mantle with there's some sort of magmatic activity that's heating up this ocean. We've got some circulation of material, and then we've got this underside of the ice leading to the surface with fissures to the surface that allow the material from inside to possibly access the surface of Europa. And so we want to understand this whole coupled system and what that means for the habitability. And of course, I mentioned this when we talked about Enceladus, but we're looking at these sorts of structures. Do these sorts of structures exist? These are black smokers on the ocean floor of the Earth. And these are basically hydrothermal vents. They're where heated, mineralized water is ejected from within the Earth's crust into the water, producing these mineral columns, and they're real sites for life on the ocean floor on Earth. So, do these things exist in this region of Europa? That's one of the gold questions we want to answer if we can. But Ganymede is the real focus for the mission, and one of the very exciting things that Galileo found at Ganymede was that Ganymede is the only satellite in the solar system to have its own magnetic field. And we can get a hint of that when we look at this picture of Ganymede, and you might be able to discern that the equatorial regions here are a different color to the poles, and that's because all of this radiation in Jupiter's magnetosphere is able to access the polar regions at Ganymede. And when that radiation hits the ice, it alters the ice, brightening it, whereas the Ganymede's own magnetic field protects the equatorial regions of Ganymede, protecting the ice from this weathering process. And we can see that in some of these, in a combination of this color picture of Ganymede with a simulation of what how Ganymede's magnetic field interacts with the magnetic field of Jupiter. So these lines here in white here, these are the magnetic field lines, and out here in this sort of cyan colored region, these are the magnetic field lines of Jupiter. Out here, close to Ganymede, these are the magnetic field lines of Ganymede. This is Ganymede's bar magnet. But then there's a region where these two magnetic fields interact with each other. And you can see that boundary between these magnetic field lines that are connected to Ganymede and these magnetic field lines that connect on one end to Ganymede and go off to connect to Jupiter, that's where all this radiation can stream down these magnetic field lines from Jupiter's magnetosphere, hit the ice and brighten it. And we can really see that in the simulation, that boundary is quite well reproduced. And Ganymede also has a weak atmosphere, and you might think, well, at least in my field, we see this sort of structure and we think that looks like Earth's magnetosphere. It looks like the pictures we draw of Earth, just in miniature. And so shouldn't there be aurora? Shouldn't we see aurora at this boundary here? Because that's what we see at the Earth. And it's lucky that Ganymede has a tenuous atmosphere that can respond to that sort of thing, that can produce an auroral response. And this picture at the bottom right here shows you an image of Ganymede's aurora in the ultraviolet taken by the Hubble Space Telescope. And this is sitting just about on this boundary here between these magnetic field lines connecting to Jupiter and purely being connected to Jupiter, not having a foot on Ganymede at all. And then one of the things that we want to try and unpick with JUICE is whether Ganymede also has a subsurface ocean. And we think it does. And you can see that sort of sketched here. We've got a core, a mantle, some sort of ice layer, a subsurface ocean, and then another ice layer. But the data we have isn't good enough to properly constrain this. And so that's one of the things that we're going to do with JUICE, is to try and unpick what's happening inside. And then the other satellite that JUICE is going to look at is Callisto, the outermost of the Galilean satellites. And in some ways, I feel a bit sorry for Callisto, because I think Callisto is really a really fascinating place, and it's got one of the oldest planetary surfaces in the solar system. You can see from this this image that Callisto is just covered in craters. And in fact, if you look at some of these in detail, you'll find craters on top of craters on top of craters, indicating that Callisto has been there for a long time, having its surface bombarded with all these meteor impacts, and it hasn't been resurfaced. Not like Europa, where it's got this sort of smooth surface where craters are erased. These craters, once you make a crater on Callisto, it stays. And so there's going to be a lot of these flybys with JUICE to look at Callisto, and I think that's going to be really exciting. Okay, so I mentioned this radiation challenge, and I'm going to finish up here by talking a little bit about where we're at with the mission. This picture here on the top left was taken by the Very Large Array in New Mexico, and what it shows you is synchrotron radiation. And synchrotron radiation is produced by electrons that have been forced to accelerate. It's a major source of energy loss in particle accelerators on the Earth. When you try and spin particles up, they basically complain by radiating synchrotron radiation. So the fact that we see this around Jupiter tells us that we've got very, very high energy electrons around Jupiter. And this represents those radiation belts that I mentioned. So here we're seeing the intense radiation environment of Jupiter in the form of radio waves. And so this has a couple of different effects. The electrons, they barrel through any shielding that you put on the spacecraft, and they can ionize parts of your silicon circuits, your internal surfaces in the spacecraft. Over time, they destroy solar cells, they destroy integrated circuits. If they happen to charge up an internal part of the spacecraft, you can end up with an electrical short, an electrical arc between parts of the spacecraft that can end up frying electrical circuits. So it's a big difficulty. I also mentioned the material from Io, and that's in the form of very, very high energy ions, so very, very high energy sulfur and oxygen. And when that sort of material hits an integrated circuit, it causes a localized defect. It can flip the sign, or it can flip memory locations in computer memory. So that means that your sort of program gets corrupted as the computer is trying to run, so the computer crashes. There are all sorts of multiple complicated problems that this causes. And so that's a real challenge. And with how they solved this with Juno, this is a picture when Juno was being constructed. That's the spacecraft that's going around Jupiter now. Their solution was to say, well, let's put all of the electronics, all of the computers, we're going to put them in a lead-lined box. We're going to put them in a there are other materials involved, including tantalum, but let's put it in a heavily shielded box. They call it the vault. And what we're going to do is we're going to put that in the middle of the spacecraft and put the fuel tanks on the outside. And therefore, we'll use the fuel tanks as additional radiation shielding. And normally what you see is these fuel tanks are on the inside and everything else is strapped around the outside. So that's an innovative solution there to try and preserve the electronics for as long as possible. That's how they solved this problem with Juno. But that gives you this planetary protection problem, is that you've got to make sure all of your electrical circuits in there don't have bacteria on. Because once you've put them inside that lead-lined box, all of that radiation from Jupiter is not going to get inside to kill off that bacteria, to kill off those microbes. And so you've got to use other very expensive methods to sanitize the inside of this box before you launch it. So that's this problem when we come to Europa. I'm going to leave you with a couple of pictures. So this is a picture, a recent picture of JUICE in construction. This is the JUICE spacecraft. This is, I believe, in France. And this instrument here is this device here is the magnetometer boom. This is going to carry some magnetometers that will look for some of this evidence for these subsurface oceans. This is the instrument I'm involved in on JUICE, and this is them basically attaching the magnetometer arm to the spacecraft. This will be 10 meters long in the end. And they're doing lots of testing and vibration testing. There's some great images and videos on the ESA website showing you various tests. There's a great video showing them testing the high gain antenna, this big dish, for vibration, to see if basically they're going to try and shake it and see to make sure it doesn't fall to bits. So there's lots of stuff that you can see of them and sort of on building that spacecraft up and testing it. And then the final thing I want to mention is that you may be aware that we've recently started to move beyond ESA's cosmic vision and into what we call Voyage 2050. And in the last month, the European Space Agency selected 3 new large missions that will follow on after JUICE has flown, after the Athena X-ray Observatory, and after the LISA Gravitational Wave Observatory. And one of those missions will be another mission to one of the satellites of the outer planets, maybe Enceladus, maybe Titan. But that's on the horizon for sort of the latter first half of this century, so leading up to 2050, as the name applies. I'm going to leave it there. Thank you very much for listening. Really happy to answer questions. I hope you enjoyed it.
Right. Well, thank you very much for that, Chris. A great update on where we are with that mission and all that's to come. If you'd like to send your questions in, there's a slight delay on the YouTube, so we'll catch up there. But anyway, I see James has got one in already, but I was just going to ask, do you think all the satellites, well, certainly not all the satellites, but all the Galilean satellites, they were created in situ, were they? They weren't captured bodies or anything like that?
I don't know of any evidence that they were captured bodies. I mean, it's very evident with Triton and Neptune that it's captured. It's in this retrograde orbit, retrograde and inclined orbit. Yeah. Whereas you need the 4 Galilean satellites are all in sort of very regular pseudo-circular orbits. Now that being said, there are lots of gravitational interactions in the system, and so they could have been circularized over time. But I'm not aware of anyone who talks explicitly about them being captured. No. Yeah, as far as I'm aware, the predominant thinking is that they're formed in situ. A lot of the smaller ones are presumably just captured bits of rubbish that was floating around. Yeah, and with those irregular, there are plenty of irregular satellites that are in these odd orbits, that are in inclined orbits that are far away and are spectroscopically distinct, and you can match their spectra to different groups of asteroids and so on. Okay. So you can tie them back. Yeah. It's quite a industry at the moment, isn't it? Detecting new satellites around Jupiter and Saturn. Every time I look, they seem to have gone up. Yeah, absolutely. Yeah, absolutely. So, right. There's a question there from James. Does the interaction of the magnetic fields of Jupiter and Ganymede have sufficient force to influence the orbit of Ganymede around Jupiter, or is it purely down to gravitation forces? That's a really good question. And the answer is yes and no. It does exert a force, but it's tiny compared to the gravitational force. And you can do the same calculation at Earth. So the interaction of the Earth's magnetic field with the solar wind and the magnetic field of the sun, that exerts a force on the Earth. And it's a relatively large force, but it's tiny compared to the other forces. Right. So yeah, there are forces in there, but they aren't sufficient to really influence the orbit. That doesn't mean to say that it will be the same for every object in the solar system, in the universe, but it's not the case at Ganymede. Because
most of it, I seem to remember most of the big moons are sort of all in residences, aren't they? Or fairly close to it. So
yes, absolutely. Yeah.
It takes quite a bit of effort to kick them out of those, isn't it? They kind of settle down and are quite happy where they are. So
yes.
you have to see. I've written down quite a few questions. I don't want to hog them all, but anyway, if there's nothing else at the moment. You said about the power usage that you only get 25th of the sunlight there. Has the improvements in electronics over the years got such that we don't need quite as much power, or is it really that you still need as much as you can get because of the?
I think you still need as much as you can get, and also then if there's spare power, then you can always say, well, we'll use it on an antenna, or we'll use it in the transmitter, or there is this new instrument is a bit more power hungry. There's ice penetrating radar and things like that might use more power. So as far as I'm aware, I don't think the power requirements have gone down at all.
No, I bet as you get better electronics, the answer is, well, we can fit more instruments on them.
Yeah.
So yeah.
But the other thing to say is that there's a margin there with the power. So you let's say you designed everything you designed your spacecraft to run on 100 watts. What you've got to make sure is that you'll have 100 watts at the end of the planned mission.
Right. And
because the solar arrays degrade with time, not just because of the radiation around Jupiter, but cosmic rays and things like that do the similar radiation damage. So their efficiency goes down with time, and so you need to say, well, we need 100 watts at the end, and the efficiency will have fallen by 5% over the course of the mission. So we need to make sure that when we get there, we're generating 120 watts or whatever the numbers might be. So there's a difference there between how much power do you have when you get there and how much power would you have at the end, and making sure there's enough headroom there to cope with anything unexpected.
Okay, we've got another couple of questions. Had one from Jane, so I'll take John's first. So thanks, Chris, for a great talk. If electrical currents flow in the subsurface oceans, they must heat the water. Is that heating significant?
Super question. People have calculated the heating. Yes, it does. It does contribute. I think people are the jury is out a little bit on it. If I remember rightly, what we don't know, what we measure is in some sense a mixture, or the measurement that we make is in some sense a mixture of how deep the ocean is and how salty it is, and we're not able to separate those two things out.
Okay.
And they separately contribute to how much heating there is.
Right.
So we don't know precisely, and it's still a topic of debate and study. But yes, absolutely, it does contribute to heating. The question is how much. But yes, it does. And this is a calculation you can do at other bodies as well.
Right.
I've done some recent work on similar phenomena at Uranus, and the models I used there don't take it into account. And so what you end up with is sort of like a lower bound on how warm the interiors might be, because you haven't taken this what we call ohmic or joule heating into effect. Yeah, right. It's just like a resistor getting warm when you pass an electric current through it. Just the same.
Oh, fantastic. James, how are the satellites sterilized on Earth before they are launched? I find it hard to believe they're totally sterile, as microbes are so prominent and hardy.
Absolutely right. Yes, absolutely. There are heat treatments, chemical treatments, and yes, you're absolutely right that there are. You can't eradicate everything, and it's it comes down to sort of probabilities and limits and thresholds. You know,
Mm-hmm.
they're built in clean rooms. You saw the picture of JUICE there with, you know, there are engineers there, and you know, they're not in hazmat suits. They're in sort of regular engineers' clothes, if you like.
Yeah.
And you know, there are filtration systems in those clean rooms, and the different clean rooms have different categories. You know, they're like ISO levels of you know, international standards on how clean a clean room is. So yeah, it just comes down to a threshold. We know it. We can't get it exactly clean, but it's at this level, and that's sufficient to meet the planetary protection requirement.
Good. Fred, given the intensity of the radiation in the Jovian environment, is there no way the electrons could be harvested for power?
Some people have talked about using a tether in that way.
Yeah, I believe that was done with the space shuttle. But,
yeah, there was some experiments with that. Yes, I'm not aware of anyone that has talked about doing that in a practical in a practical way, in a sort of a live mission, rather than let's try this as a technology demonstration. Right.
Yeah, I guess you know what you're dealing with solar panels, whereas this is a bit out there.
Yeah, and it becomes a bit of a risk, and I think that the experience with Galileo and that antenna, you know, that's essentially a single point failure, and so if I remember rightly, it was sort of decided at that point that no single point failure risks would be used again.
Right.
You know, so for example, there's been tests in Earth or between the Earth and the Moon for laser communication, and because it's at a much shorter wavelength than a microwave, you can get a lot. Your data rate goes a lot higher.
A lot more bandwidth, yeah.
Yeah, so your bandwidth goes up compared to a large dish. And so they've done these tests near Earth, but they don't want to do it at Jupiter when it might
quite accurate, I think.
Yeah. So yeah, there is I think some understandable reticence at using anything that's a bit that might cause a problem.
Yeah. Very good. That's all ones I see in the chat.
I'll chip in with one if that's all right. I'll chip in with a quick one if that's all right. Yep. I noticed that Juno's gone quite close to Ganymede in recent times. Did any new science come out of that, or is it still too early?
I'm not plugged into the Juno mission, so I don't know I don't know anything beyond the images that were reported to the media. So I don't know exactly how close it got to. You know, for example, I don't know if they get close enough to go through that region of Ganymede's magnetic field. Mm-hmm. I haven't stayed enough up to date with it to know exactly what's been reported. I'm at a conference in a few weeks' time, so maybe I'll find out there. Where we're going to get an update on current missions, so maybe we'll hear something there.
And what's the end game for JUICE? Is it just staying at Jupiter? I presume it's not able to go further out if it's solar powered.
No, it will. Once it's in orbit around Ganymede, it's in orbit around Ganymede, and so the idea is once you're in the circular orbit will be lowered to a much lower orbit, and then eventually will just touch down on the surface, a little bit like Rosetta did.
Okay.
On Comet 67P, just come to a rest on the surface.
Right. So potential images of the surface from it.
Potential images of close-up images of the surface. Right. Yeah.
And what sort of time frames that then?
That is in the. I just go back to mine. There's a timeline there.
So that'll be a first for Ganymede, I would imagine.
It will be a first for Ganymede. So that's in 2033.
Okay. Save that date.
Yeah, right.
Glad in your diary
now.
Yeah. Great.
Are there any further projects to go to, further out planets like Uranus and Neptune? Anything like that on the horizon? Horizon 2050?
So plenty of people want to, including myself, and it was mentioned in the Voyage 2050 plan, but without anything firm. Right. You may have heard that NASA's just selected two Venus missions, and one of the competing missions that was rivaling those was called Trident, which was to go out to Triton.
Ooh,
but that wasn't selected. So people keep wanting to make it happen, but it's not happening yet. And there's a favorable launch window to Neptune with a gravity assisted past Jupiter, but that's closing very rapidly. I think that launch window is in the mid 2030s, early 2030s, I think. That basically that's 10 years out from now, and that's relatively short order to design, test, build, go through all of the motions, get it on a rocket and launch it. So that opportunity is closing rapidly, if not already closed.
Right.
But that still leaves Uranus open.
Yeah. Because we have been there since 1980s. Was
Flyby Uranus in 1986 and Neptune in 1989.
Technology must have moved on a bit since then.
Technology has moved on a bit, yes. Yeah, it's a long time ago.
Yeah. Well, I think that's all the questions. So remains to thank you very much for giving up your time tonight, Chris, and bringing us up to date on this. So we're all very grateful for that.
You're welcome.
And, maybe next time you present to us, if you do, or if you have time, it might even be in person. Who knows?
Maybe, yes. Maybe that would be nice. That would be very nice.
Would be great. Well, thank you very much for your talk tonight.
Thanks very much for having me again.
Great. Right. Any final closing things, Richard?
Yeah, just a quick reminder. I'll send out a hard copy of the journal as soon as this meeting's finished. So look out for that in your inbox. Coming shortly. So next meeting on Thursday, the 15th of July. So we're going to do that one hopefully live from the observatory, streamed onto YouTube. So
cross your fingers, everybody.
A good challenge for us. Let's hope for a good internet connection up there.
Yeah, let's hope.
It should be fine.
And then the barbecue on 7th of August, 5 p.m. As long as the weather's looking fairly reasonable, basically. We got a reasonable amount of shelter, and so we can weather a few minor storms. But if it's looking awful, we might just watch this space, basically. That one.
Well, I think you've got the talk planned, don't you? If you want to say something about that for December now as well.
Oh yes, we got a talk book for December. It's Pete Williamson from Shropshire, I want to say, Oswestry, and it's called Herschel to Hawkwind, and it's a combination of astronomy and music, because he's both an astronomer and a musician. So he's looking at music that has inspired space, and space that's inspired music, and a bit of an interesting mixture for Christmas, I think. So that should be fun. Hopefully in person, but we will just wait and see. As ever, being the tagline for this year. Right. If there's nothing else, oh yes, there you got it there. Herschel to Hawkwind. Thank you very much. Yes, 2nd of December. Brilliant. Right. So with that, thank you everybody for attending, and we'll see you next time. Hopefully on the 15th, we'll welcome you back. Until then, good night from me.